Hello world, and welcome to the Computer Scientist channel. In the first video of this series on the client-server model and programming, we introduced connected applications made of several interacting programs. We also introduced the client-server model and programming as their foundation. In this second video, we'll start with the following basic concepts: clients, servers, connections, and the socket API. By the end of this video, you will be able to address misconceptions about clients and servers. You will also be able to explain clients and servers in technical terms, how client-server connections are established, the central role of the operating system, the purpose and the power of the socket API. Finally, you'll be ready for the next video about Java and Python socket APIs. We aim to write two programs, A and B, that will run on two machines and collaborate to achieve a common goal. For example, they would allow sending and receiving chat messages, sharing files, or knowing how much processing power the other side has. At runtime, a program is modeled by the operating system as a process, so we'll be using this term when referring to running programs. Back to our objective, the communication between the two processes gets down to I/O operations, whereby data written by process A as output is read by process B as input, and vice versa. As such, we can draw the analogy with an I/O operation you're already familiar with: writing data to a file. But before doing so, several questions arise. Does the file exist at all? Which mode of operation are we requesting? Read, write, or append? Are we authorized to access the file under such a mode? How are several write operations coordinated so they don't step on each other's toes? Addressing these questions requires establishing a context and a state before issuing any operation. This is why we need to open the file first, and while performing the operations, the state is continually updated. For example, the file cursor is advanced accordingly. Notice that we can open several instances of the same file in the same program. Each instance has a dedicated context and a dedicated state. Similarly, before two processes can exchange data, context and state must be established on each end and bound together on their behalf by their respective operating systems. This is what we call a connection. We say that a connection must be established between the two communicating processes. Here, the connection is an end-to-end concept. The underlying network is unaware of it. This shouldn't be mixed with a Wi-Fi connection or a XDSL connection. Back to the analogy with files. For a file to be opened, it must be identified first. To this end, we specify its path. Similarly, for a connection to be opened, its endpoints must be identified. So what would be the equivalent of the file path for a connection endpoint across the network? First, we need to identify the machine, and that's the IP address. But then, on the same machine, the operating system may manage several connection endpoints, whether belonging to the same process or different processes. Therefore, we need additional information to discriminate between them. This is a unique number assigned by the operating system to each endpoint. We call it port. So, a connection endpoint is identified with the IP address of the machine and the port that the operating system assigns to the endpoint. The port is an unsigned 16-bit integer, so its values range from 1 to 65535, 0 being reserved. Pause the video and take a few minutes to assess your understanding. You can share your answers and thoughts in the comments below. In all that we have described so far, the operating system plays a central role. It manages ports and grants them to processes while ensuring their uniqueness. It manages connections on behalf of the communicating processes. It abstracts away the networking details and the hassle related to data traffic. Thanks to the services and abstraction provided by the operating system, establishing connections and exchanging data between processes become as simple and easy as dealing with files. We access these services and enjoy such an abstraction thanks to system calls. Examples of system calls include reading input from the keyboard, allocating space in memory, opening a file, reading from or writing to a file, closing a file. In particular, the set of system calls to allocate a port, open a connection to a remote process, perform network I/O operations through a connection, close a connection, release an allocated port, are grouped under a standard API called the Socket API. It was first defined in C programming language at Berkeley University and released in 1983. Other programming languages provide their Socket API as wrappers around the original C Socket API. In the next video, we will cover in detail the Python and Java versions. Pause the video and take a few minutes to assess your understanding. You can share your answers and thoughts in the comments below. With all the background acquired so far, let's see, step by step, how the interaction proceeds between the two processes. Process B starts and asks its operating system to create an endpoint identified, let's say by port 7000. The operating system checks whether port 7000 is free, and in this case, grants a corresponding endpoint for process B. Then process B asks its operating system, listen to incoming connections for me. On the other side, process A starts and asks its operating system, open a connection on my behalf to the endpoint IP B, port 7000. First, OS A creates an endpoint for process A with a free port, for example 1234. Then, it sends a connection request from the endpoint IP A, port 234, to the endpoint IP B, port 7000. OS B receives the connection request and verifies whether it has a process listening on port 7000, and this is the case. Then, it sends a connection acceptance to OS A. OS A receives the connection acceptance and creates the connection's context and initial state. Then it sends a connection confirmation to OS B and returns a connection handle to process A. OS B receives the connection confirmation and creates the connection's context and initial state. Finally, OS B returns a connection handle to process B. At this point, the connection has been established between the two processes. Now, they can start exchanging data using their respective connection handles, just like writing to or reading from an open file using its handle. At some point, process A or process B may decide to close the connection. The context and state are cleared on both sides, and port 1234 is released on system A. Process B may still accept more connections from other processes. From this interaction flow, we can notice that processes A and B didn't play symmetric roles. Indeed, while process B selected and requested a specific port from its operating system, process A was assigned an arbitrary port by its operating system. Moreover, while process B opened the connection passively by accepting it from its operating system, process A opened it actively by requesting it from its operating system. Finally, notice that the two processes can't play symmetric roles because, for a connection to be established, one process should be willing to accept it, while the other should request it. In this scenario, process B acted as a server and process A as a client. A server is a process that selects and requests a specific port and the creation of the corresponding endpoint. It opens connections passively with clients by listening to and accepting incoming connection requests. A client is a process that opens connections actively with servers. While doing so, it gets granted arbitrary and free ports. The client should know the server endpoint before opening the connection, while the server doesn't need to. It discovers it when it receives the connection request. This figure shows two clients connected to the same server. Notice that the second client has opened two connections to the same server. Notice also that the three connections have the same server-side endpoint while being issued from different client-side endpoints. We stress again that clients and servers are processes, not machines. A machine may run several clients and servers. Also, what distinguishes clients from servers is not the data flow direction, but rather the connection opening mode, active for clients and passive for servers. Once the connection is opened, data may flow from servers to clients, from clients to servers, or in both directions. Pause the video and take a few minutes to assess your understanding. You can share your answers and thoughts in the comments below. In the next videos, we'll cover Java and Python socket APIs. We'll also learn that client-server interaction is more than just I/O. This is why we need protocols, and we'll talk about them and their vital role in detail. Finally, we'll cover a real-life case study whereby we'll design and implement an interesting client-server application called FX. I hope you're enjoying our step-by-step journey toward demystifying the client-server model and programming. To level up as a computer scientist, show love and appreciation and hit the subscribe button.